Okay, Unit 7, equilibrium. We are now on question number 46. Okay, let's go ahead and get to the question. All right, number 46, it says, how many moles of NaF must be dissolved in 1 liter of saturated solution PbF2 at 25 degrees Celsius to reduce the Pb2 plus to 1 times 10 to the negative 6 molar? Okay, so we've been given some numbers. That KSP has been given to us, and notice how I already set up our KSP. Our KSP is 4.0 times 10 to the negative 8. Our PB is equal to 1 times 10 to the negative 6. And we're just trying to find the concentration of our F, but our F is squared because this coefficient of this 2 becomes a exponent in our K expression. So, all right, what are we going to do? We're going to get this and we're going to divide this onto the other side so that we can get X by itself, okay, which turns out to be 4 times 10 to the negative 2 is equal to X squared. How do we get rid of the squared? Well, very simply, we square root both sides. Now on this one, let's just square them individually, think of square root of 4 and square root of 10 to the negative 2. This becomes 2, this becomes times 10 to the negative 1. The correct answer, therefore, is D. Not bad. By the way, what we really actually solved was molarity, but since it was over 1 liter, it is also our moles. So that's kind of a step we didn't need to kind of go to, but I do want to be clear. I did solve molarity here, not moles, but it's an easy transition when you have 1 liter. Okay, number 47, let's just skip. Okay, I don't know what the heck's going on there. Like, not all of it, printed out, so what is happening? All right. Number 48. Which of the following statement best helps to explain why the contents of the tube containing equilibrium mixture turned a lighter color when the tube was placed into an ice bath? So let's go back to this. Okay, so we need this thing. We need to understand why at an ice bath did the thing turn, did it say colorless? Yeah. Why did it move towards being a lighter color? Why did it move towards becoming colorless if we place it in an ice bath? Well, what would an ice bath do? It would lower the heat, okay? So I want you to think of this in terms of exothermic and endothermic, because that's how temperature affects equilibrium, right? So if we had an endothermic reaction and heat was if we had an endothermic reaction and heat was a reactant, and we put it in ice, then you lower the heat, right? You got rid of heat by putting it in ice. Wow, that's really ugly. But okay, so what would the thing have to do to get back to equilibrium? It would have to produce more of this product. Ugh. It'd have to produce more reactant. Man, I'm screwing up all over. All right, so if you lower the heat on an endothermic, it will create more reactant. And that's what we're trying to do, because if we create more reactant, it becomes lighter in color. It becomes more colorless, less brown. So the correct answer is B. The forward reaction is endothermic. Heat was a reactant, not a product. Okay, number 49. Okay, we got to calculate K5. So let's look at K5 right here. Okay, what we're going to do is we're going to break these apart. Okay, so I'm going to see kind of like Hess's law. I see this H2CO3. I see an H2CO3 here. I see a HCO3 minus from that HCO3 minus. I see an NH4 plus and an NH4 plus. And I see a NH3 and an NH3. See, all that stuff comes from equations K1 and K3. So I know I have to have K1 times K3. However, how do I get all this other stuff to cancel out? Like this H2O and this H2O and this H3O and this OH. Like, how do I get all that stuff to cancel out? Notice I have H2Os here, and I have an H3O here and an OH here, but they're all on the wrong side. Look, I need these H2Os. I'm using purple. I already used purple. I need these H2Os over here to cancel out with this. That means I need to flip the bottom one. But when you flip a K expression, you go 1 over K to the fourth. You do the inverse of it. So I have to have K1 times K3 also times K4. Look at your possible answer choices. And there's A has that K4 in the denominator. That is your correct answer. Number 50. Okay, AJCl yields AJ and Cl. The KSP is really small. Shown above is information about the dissolution of AgCl in water at 298 degrees Kelvin. In a chemistry lab, a student wants to determine the value of S, the solubility of AgCl, by measuring the Ag plus in a saturated solution compared to mixing excess AgCl in distilled water. How would the results of the experiment be altered if the student mixed SS AgCl with tap water? Okay, if you added extra AgCl, you're going to increase the Cl minus, right? Like you're going to have more of this there. If you have more of this there, like you're going to have more products than you should. So if you have since you already had Cl minus in the water, the value you would have too much product over reactant, and you would end up over creating the reactants here. So the correct answer is B. The value of the obtained KSP would be too small because less AgCl would be able to dissolve. Like because you already have AgCl in the water, less of this could happen, and then your numbers would be off. This is the common eye effect due to the Cl minus that's already in the water, because the Cl minus, like think of it as like an ice table. Like you have an initial amount of AgCl, but then you would also have an initial amount of Cl minus in the water as well. That's making your numbers skewed. All right, number 51. This one, it felt like it was going to be a lot of work. I'm glad the answer came early. Okay. The equilibrium constant for the dissolution of KSP for various substances in an aqueous solution at 25 degrees Celsius are listed in the table above. Which of the following provides correct comparison of the molar solubilities of S of some of these substances based on their KSP? All right. Look, your molar solubilities is how many moles how many moles of your positive ion and your negative ion, are going to be diluted. Now, here look at number 1. It says the molar solubilities for Cu and Cn and Ni and Cu2 are calculated by this. That's true, because look, this is your Cu2 plus, this is your Cn minus, and these are both the same number, right? So they're really just x squared. So if I want to find my solubility, or how much of my Cu or how much of my Cn, all I need to do is square root both this and square root both this. So look at A and B. They both have the solubilities equal to the square root of K. So that's true. Okay, this part is true. The molar solubilities of CuCN and NiCO3 are calculated by S is equal to radical KSP. That's true. And NiCO3 has a lower molar solubility. Let's look. NiCO3, CuCN. Who's lower? CuCN is much lower. That exponent is a negative 20. Okay, so no, A is incorrect. The molar solubilities of CuCN and NiCO3 are calculated using that, and CuCN has a lower molar solubility. That is true. That makes C and D automatically false. The answer is 50. Or for 51 is B. All right, let's get to 52. Barium iodate. You have barium, 2 iodates, the KSP is that. According to the information about the dissolution of barium iodate shown above, the correct value of S of the molar solubility of BaIO3 can be calculated using which of the following mathematical. Okay, so let's do the BaIO3. We have barium iodate, this is to the 2, which is going to yield Ba2 plus and IO3 minus, and there is 2 of these. Now your KSP, on the other hand, KSP is equal to the concentration of your Ba2 plus times the concentration of your IO3 minus squared. But look, this 2 coefficient does that, but it also does another thing. Look, if I had, this is a tangent, but if I had 100 of these, I would have 100 Ba2 pluses. But I would have 200 of these. I would double that number. So this is becoming x and 2x squared, okay? So, okay, I really want you to get this point. This 2 becomes the coefficient, and it becomes the concentration here. Okay, that 2 does 2 things there. Now, we're going to set that equal to your KSP. You're going to have 4 times 10 to the negative 9. And don't worry, you're not going to have to manipulate this, but they do want to find the molar solubility. So in other words, we got to get x by itself. This side will, again, become this very famous 4x cubed. This is it's not every question doesn't do that, but a lot of them do. Okay? So you have 4x times 10 to the negative, this, okay? What looks like that? The answer, D. Okay, this is that, this right there, this 4x to the third is shown here. All right, that's number 52. Let's move on to number 53. 53 is a similar type problem. Okay, same thing here. The KSP of this is going to be the concentration of Ag, or 2 Ags. That A is really ugly. Let me rewrite that. And the concentration of only 1 CO3 2 minus. This is going to be x. This is going to be x squared, and this is going to be x. But notice that that x is going to be double the concentration. So again, you're going to get this 4x cubed equal to your KSP. Well, whatever your KSP is, we're going to divide it by 4. KSP, we're going to divide that by 4, and then we're going to cube root it to get x by itself. That correct answer is D. So dealing with KSP, you got to remember that the K never has a denominator because solids don't play in equilibrium. And if you have 2 of like an ion, for example, here there's 2, that 2 right there, it's going to not only double the concentration of it, it's also going to square it as its coefficient. Okay. H2 gas and N2 gas are placed in a rigid vessel and allowed to reach equilibrium in the presence of a catalyst according to the following equation. You have the Haber process here, 3 H2s plus an N2 yielding 2 NH3s, and it is an exothermic process. The diagram below shows how the concentrations of H2, N2, and NH3 of the system changed over time. Okay? All right, what's the question? More NH3 is added to the system at time 2 when temperature is held constant. So it's at equilibrium, and NH3 is a product, so we're going to add more NH3. If we add more NH3, it goes like this. It crashes on the right side. While the temperature is held constant, which of the following most likely to occur? If we, remember, when temperature is held constant, equilibrium constant cannot change. Okay, so that A and B are gone. The total pressure of the container will decrease. No, the total pressure of the container will increase because we're adding more gas, more collision. The amount of N2 will increase. Yeah, the amount of N2 will increase because this will create more reactant because we just stressed the right side of it. So the answer is D. That is correct. All right, number 55. Which of the following was true for the system between time 1 and time 2? Between time 1 and time 2, look at time 1 and time 2. What are we at? We are at equilibrium, okay? Which equilibrium is not when the substances are equal, it's when the rate of the forward reaction and the rate of the reverse action are equal. So, which of the following for this system between time 1 and time 2 is true? Okay, A, the concentration of N2 decreased. No, it's going to stay the same. The temperature of the system decreased. That better not be true. The number of effective collisions between H2 and N2 was 0. No. They're still reacting. They're just reacting at the same rate. D, the rates of the forward and the reverse reactions were equal. That is exactly what we call equilibrium. That is correct. Answer here. D. Let's move on to 56. Okay, again, we have the Haber process. It is exothermic. NH3 was synthesized in 200 degrees Celsius in the presence of powdered OS catalyst, leading to the equilibrium system represented above. Which of the following changes would result in more NH3 in the mixture after the equilibrium is reestablished? So what would do this? Okay, because that would make you create more NH3 because you're, yeah. All right. Replacing the powdered OS with a solid cube of OS. That, I mean, you're losing surface area, so no, that doesn't have anything to do with it anyway, or I guess. And then, okay, increasing the temperature of the system. We said that this is exothermic, so heat is a product. Heat is a product. If we increase the temperature, it would make it go like this. That's the wrong way. Removing some H2. If I took out H2, it would also look like this because H2 is a reactant. The correct answer is D. If I added N2, because N2 is a reactant, if I added more reactant, then this would happen and I would have to create more NH3. All right, 57. What's the value of the equilibrium constant following this reaction? Look at this thing. Look how this N2O5 and this N2O5 are there. Your NO2 and your NO2, and then your O2 and your O2. But what's the difference? The bottom equation is not only flipped, it's doubled, right? So if this is K, you got to flip it. It becomes 1 over K, and you got to double it, which becomes 1 over K squared, right? So this is 1 over K squared. And the question told us that 95 was the K, so the answer has to be E. You had to flip it and you had to square it, okay? It's not Hess's law. Hess's law, when you flip it, you just change the sign, and when you double it, you just multiply it by 2. Here, when you flip it, you make it the reciprocal, and when you double it, you square it. 58. All right, we reached equilibrium somewhere around 60. All right. A sample of NO2O4 is placed in the evacuated container at 373 degrees Kelvin and allowed to undergo the reversible reaction of N2O4 and yields 2 NO2s. The concentration of each species is measured over time, and the data are used to make the graph shown above. Which of the following identifies the equilibrium is first reached, provides a correct explanation? At 14 seconds, N2O4 is twice NO2. Well, that's believable, which implies the forward and reverse reaction rates are equal. No. We know that the forward reaction rate is going to be faster, and this is going to be slower, and that's why it's going to get to equilibrium at some point. At 23 seconds, NO2 equals N2O4. That looks believable too, which shows that equal concentrations are present at equilibrium. This ain't equilibrium. This is not equilibrium. This is the part where they cross. Okay. C, at 40 seconds, NO2 is twice that of N2O4. I guess that's believable, which makes the stoichiometry of a balanced chemical equation. No. What is happening there? All right, the answer is D. At 60 seconds, N2 and O2O4 remain constant, indicating the forward and the reverse reaction rates are equal. This is the definition of equilibrium, wherein the forward and the reverse reaction rates are equal. And at 60 seconds, yeah, we are now at equilibrium. The reaction rates forward and backwards are going to be equal. 59. Wow. Reactions 1, 2, and we're going to try to figure out what reaction 3 is. Again, kind of doing this Hess law thing. We have this Haeckel over here, and then we have a Haeckel over here. We have, let's see, Haeckel over here, and we have Haeckel over here. So the first thing that I know is I need to flip number 1. So that has to become 1 over K1, like it has to become the reciprocal of it. Okay. Now, I need this OH minus to line up with this OH minus. And, well, I guess I need one of these O2s. Like I need these H2Os to line up with that H2O. Now, here's the thing. What did I have to do the first one? I had to flip the first one, but I don't want to flip the second one. So I'm going to have K1, 1 over K1, and I'm going to have K2 here. So this is going to be 1 over K1 times K2. The correct answer here, let me see, is A. Yep, that's it. All right, number 60. At a certain point in time, 1 liter rigid container vessel has 1.5 moles of PCl3, 1 mole of Cl, and 2.5 moles of PCl5. Which of the following describes the measured pressure in which the reaction vectors would change and why? All right, let's do the K. The K here is equal to PCl5 over PCl, and PCl3 times Cl2. Okay, let's plug in some numbers. The PCl5 is going to be 2.5. You're going to, PCl3 is 1.5, and Cl2 is 1.0. You know how I like to do, okay, let me show you how I do this math in my head without a calculator. Not that it's all that hard, but I know that this is 5 halves over 3 halves times 1. So really, I'm just going to multiply it by the reciprocal. So I'm going to be 5 halves times 2/3. This cancels out. And then I have 5 over 3. 5 over 3 turns out to be 1.6666. So in other words, that's not important. Okay, the 1.6 is less than the Kc. So the Q is less than K. So it can't be D, it can't be B. The pressure will increase. Okay, if you have Q is less than K, it wants more product. If it wants more product, if it wants more of the PCl5, right, it needs a greater numerator. So if you form more of this stuff, this is only 1 mole on this side. There's 2 moles on this side. This stuff will go away, so your pressure will decrease. The answer is C.